Hello students, today we will learn about state table reduction. In our earlier class, if you remember, when we read about combinational circuits, we used K-maps and we used QM method to optimize the combinational logic circuits. So in state table reduction also there are few techniques wherein we can optimize the sequential circuits also. So those techniques I'll be introducing you today. So this was something which we did in the last class, where we had to detect a sequence. The input was a sequence of numbers which were coming, and we need to detect the sequence properly. That is 1001 was the question which was given for as an example. So when this particular sequence of numbers were binary bits were received, the output was required to go to high. So we made an state chart like this, and then we made the present state, next state, and then we decided the y should be 1 when the state receives. State is S3, and then you receive another one as an input, so the output used to go high. So this was something which we discussed in the last class, and then we followed it up by making an circuit. So from here, from the values of y, we decided to use an D flip-flop, and then we made a circuit out here. Okay, so there could be an complex. That was a very pretty simple circuit in which probably there was no option for optimization. But when we think of some big circuits like this in the state diagram, we are not sure, but just by seeing the state diagram, we cannot say if this is the most optimized way. Is there any way to identify if we can further optimize it? So we need to learn some techniques for that. Okay, so this could be a problem like you are writing a program for say Swiggy. You are initially at 0 state. Okay, you are going and browsing a particular dish, whatever you want. Say you want to buy a dosa, so you are in state B. From there, okay, once you have selected dosa, you come to a next state where you select your payment option, and then you pay. So this goes 1 here. So okay, you have paid it. Alternatively, after having selected and dosa, probably you can go for the rating of that in a particular hotel, and if it is not good enough, you can go back to A, and if it is 1, and you come back here, make a payment. Okay, or other the option is once you have selected here before, once you make the payment, before making the payment, you want to go and see if there are any offers available. If there is an offer available, you take that offer and you come back here. Or if there is no offer available, probably you want to go back to the home page again, start looking for another dish. Okay, and even after the payment, maybe there is a confirmation button. If you want to confirm it, it says yes, you come back here. If you say no, probably you go back to the home page. Okay, so you might be thinking, what is this to do? Ultimately, even when you write a program on your laptop and you launch it on your web page, okay, somewhere in the world some server has to implement this, right? This circuit to get you the desired results. So many times we think, okay, we are just writing programs and we'll get the results, but that doesn't happen. Somewhere in the world, okay, if you're writing it in the web, maybe it goes to that web server, and in the program will run in that web server. So that particular server might convert this state table into an hardware somewhere. So this hardware is required, right? So this is how we have taken one complex example. Now what we are going to write is A, B, C, D, E, F. This is the present state, right? Okay, now we have remember, we have not yet assigned any flip-flops for these things. Okay, we just read the English literature and we made some states, okay, accordingly right here. So the number of flip-flops to be used and what is the value to be given for A, B, C in those flip-flops, that we will decide later on. Presently, just the problem statement has been mapped into an state chart. That's all. From the state chart we are going to make a state table. So this is the present state table. You have A, B, C, D, E, F, G. This we have done in the last class, so we are going to do exactly the same. So this is the next state. This is the input. So input could be either be x is equal to 0, and the output could be x is or the input could be x is equal to 1. If it is x is equal to 0, A remains here, so A remains here. And if the input is x is equal to 1, it goes to B, right? It goes to B. So this is how we are going to map. And in this case, either even if it is 0 or 1, the output continues to remain 0 here. So we have written for x is equal to 0 and x is equal to 1, the output is 0. Okay, this is only for state A. Similarly for B, C. Okay, let me read out one more for B also, so that there is no doubts. So for the B, if you see, if the input is 0, it is going to C. It is going to C here. If the input is 1, right? If the input is 1, it is going to D, and it is continuing to remain 0. So it is D, it is continuing to remain 0. For D, if you see, for a case where if the input is 1, the output is going 1. For D, if the input is x is equal to 1, the output is going up. So exactly whatever we have drawn the state diagram, we have represented it in the reduction table. Now after having done that, so if you see these variables, even visually, this is known as state table reduction. We can call it is equivalent to a K-map. Okay, where with visual clues you can straight away reduce it. So if you see, is there anything which is very common in these things? If you see AF01, that means for a state E, it's just a state. Okay, it's not at an hardware, it's just a state E. If x is equal to 0, it moves to A, and if x is equal to 1, it moves to F, right? And if it is G also, it is exactly the same. So, and also the outputs are same. It is most important. Even the outputs have to remain same, right? So if you see, these two states are exactly so the one can be rendered. This is an redundant expression, so we can remove that state altogether, right? So what we are going to do is we are going to cut this off. Now when we cut this off, you have one residual G out available here, right? So because no more we are not going to have that state at all, so we are going to since we are going to retain E and G, so we are going to, wherever there is a G, we are going to replace it with E, right? We can also cut E and retain G also, either way, right? So in that case, all the E's have to be replaced with G. Now what we have done is, since they both are same, exactly the same, we have cut that row in totality and changed the value of G to E, right? Okay, so if you see here also, this G would go off, right? It doesn't matter. Now what was happening to F, it was a 0, it was going to G, right? And then another 0, it was going to 0. Now you are going to remove G and I'm going to put E. So here what happens now, again F is equal to 0, it will go to E, and another 0, it goes to A. Same thing exactly what is happening. What was happening here? After going to G from F, if I was getting one more 1, I was coming back to F. Same thing, if I go to E, if I am getting one more 1, I will come back to F, right? So it is equivalent. So there is no point having both these two things. If you see this state diagram, the same thing here, watching this diagram also you can do that, but it becomes much easy when you do it in the form of a state table reduction. So I am going to remove this G here, right? Now this is going to be my reduced state there, where I have removed off the G and kept only E and F. Now again I do a visual check, is there something which is in common? So if you see D and F, right, they are exactly the same. So what I am going to do is I am going to again remove F, right? So understand that not only the inputs, even the outputs have to be mapped only then. So I'm going to remove this. So, and then wherever there is an F, I am going to replace it with D, right? So now I am going to replace this F with D, and I'm going to replace this F with D. So this becomes my, now there are 1 2 3 4 only 5 states. So this is the final expression, if you see, right? And further reduction is not possible out here, because if you see A B C D A D E D A D, right? AD is common here, but then the output conditions are different for those two, so you can't merge. So this is one way of getting an reduced state table reduction. This is the method 1, right? Now the second method also, what we are going to do is, okay, now after having done the state table reduction, now you can you need to assign those states, okay, some flip-flops for them, right? They are known as the state assignment, right? So what can we do? Like there are 5, so at least 3 bits we require, right? 3 flip-flops you will require, because to generate 5 different states. So we take, so like we did in the last example, it was a pure binary sequence we assigned. Now 0 1 2 3 4. You could also assign 0 1, okay, like a gray code. You can also assign a gray code, right? So, and you could also use 5 flip-flops and give this kind of assignments also, further representing each of these states, right? So it doesn't make really any difference. The solutions for these things will be slightly different. The combinational logic, which this, if you take this assignment, it will generate one kind of combinational logic. If you take this, it will generate one kind of combinational logic. If you take this, it will generate the third kind of combinational logic, right? So you just have to, if I go back to my first slide, so you, whatever you take this, like 0 0 0 1, whatever state you take, these here you have assigned pure binary. So accordingly the next stage will change. If you swap these values for S2 as 1 1 and 1 0, here the next state values will change. So that's all the difference it is going to be, right? So now similarly, if you're coming back here, so you can assign any kind of values. So there is no fixed rule for that, nor it has been proved that one of these techniques will be better, right? For it depends on problem to problem. In a particular sequence, this could give the best results, and for a different problem, this could give me a best possible combinational logic, taking least number of gates. So there is no technique, or there is no formula which will give me prior information what would give a better circuit. It is only that you need to try out one of these, or maybe randomly also you could give some values out here. Okay, only thing is each state has to be unique. That's the only thing you got to take care, right? So that is how you find out what is the best possible solution. Okay, so now coming to the next one, what we are going to learn is implication chart. Like in the previous state, like it may be equivalent to your QM method. Here if you see, you can't straight away see there is a scope for further simplification, right? Further reduction. Everything is different out here, right? S3 S2 S2 S1 S1 S3 S3 S0 S0 S4, everything is different. So you it appears in the first view that nothing can be simplified here, but that is not the case. So what we need to do is, we are going to write on the x-axis S0 S1 S2 S3. The last state is not there in the x-axis. In the y-axis, starting from the top, you write, you leave the first state. Okay, you take from the second one and you come to the last. Okay, I'll repeat it. In the x-axis, you start from S0 and you leave the last one, right? S4. And here you start from the S1 from the top, and you're leaving S0, so you come here, so you get a 4x4 kind of matrix. Okay, now you have got that. Now let's try and map S0 and S1. Okay, is there any possibility of now merging them into one, right? So this cross, we'll see we'll just see the outputs, okay, required. What is this output required for S0? It is for A is equal to 0, it is 1, and A equal to 1, it is 1, right? Whereas for S1 it is 0 0. So obviously S0 and S1 in any circumstances, okay, whatever may be the case, they cannot be merged together. So those states have to be independent because the outputs are different from those two states. Okay, the next the output from those two states are different, so I put a cross. What about S2? Okay, let me go to the I am again comparing S0. This vertically I am going to compare for S0, right? So S0 first S1 I will compare S0 with S2, S0 with S3, S0 for S4. Now comparing it with, now I am going to compare it with S2. So what happens comparing it with S2? If you see, it is 1 1 and the output is also 1 1, right? And now I am going to compare S2 and S0. So in this case I am going to replace S2 with S0. So what happens? This is S3 S0. So and I am going to compare I am going to replace. I told you we are going to try and see if these can be merged together. So what we are going to do is S3 S0 and S0 and S2, right? We are comparing S0 and S2. So S3 will remain like that, right? S2 and S0 we are going to merge. So maybe this S2 is also going to become S0. The outputs are also same, right? So it is possible. So I put a tick there, right? So let me explain once again why I have put a tick here. I am trying to find out, is there any possibility for merging S0 and S2, right? S0 is S3 S2. So if I merge, this will become S0. The outputs are same. S2 also I am going to merge, right? So here S3 S0 1 1. So it perfectly matches the condition. So I am going to put a tick here. Right now, between S0 and S3 the outputs are different. Between S0 and S4 the outputs are different. So I put 2 cross here. So it has become S0 here. Now I am taking the next element, which is S1, and now I am trying to see if I can merge it with S2. If you see, the output is different, right? So I straight away put a cross here. Okay, now I am going to compare S1 with S3, whether they can be merged. Okay, now the outputs are same, right? So there is a possibility. Now if there is a possibility, then what? Then you have to also see whether these are the inputs are the same. I am going to merge S0 and S1 and S3, whereas here it is the inputs required for these states was S0 and S1. So I am going to write S0 comma S1. This means if at all S0 and S1 become equivalent, then I can merge these two. So it is a conditional. Okay, as of now it is a conditional probability of getting these two merged. So I am putting S0 and S1 here. If this condition is somehow met, then I can merge S1 and S3 because the outputs are matching perfectly, right? Now again, between S1 and S3 these outputs are matching. It is S4 here and S3. So there is also one more condition, that S3 and S4 also have to be equivalent. Only then I can merge. Okay, so similarly I take S1 here. I am going to now compare it with S4, S1 and S4. It is 0 0 and 0 0. That means there is a possibility of merging these two. But what is the condition? Between S0 and S2, they have to be equivalent, and in that case it can be merged. So I am writing S0 and S2. I am not writing S4 and S1 also. That is also one of the conditions, because anyway I am going to merge these two, so I don't have to write it as a separate condition here. Like here we didn't write merging of S0 and S2 as a separate condition, because as such it is getting merged here. So in the same way, for S0 and S4 I am just going to write S0 and S2, S0 and S2, S4 and S1. It is, understand, we are talking about the very same possibility. So that is the reason we are not going to write anything here, right? Again I take the third one, S2, and comparing with these two. Obviously these two are different output states altogether, so straight away I put cross here. Now coming to the last state, S3. Okay, the outputs are matching out here, right? The outputs are matching here. So I need to write what are the conditions. S1 S2, right? They have to be equivalent, and S3 S1, S3 S1, that is I have written as S1 S3. So these are how, if these conditions are met. So this is the first iteration. In the first iteration, first of all you have put all crosses, so that in those cross boxes those combinations are not possible at all. So merging of those states are totally not possible. Then I have put tick here. I have put a tick here. That means this combination is very much possible. So that's why I put these 1, 2, 3 boxes. I have written something here. These are the conditions. If these conditions are met, then they can be merged. Okay, now we'll do the second exercise, like S0 S1. Okay, that's the first iteration. The second iteration I'm going to see S0 and S1. We know that they cannot be merged here, so this condition we will have to see if S0 S1 is available somewhere here. So there is an S0 S1 here, so that means this condition can never be met, because already we found out the outputs are different, so this cannot be merged. So I'm going to put a cross in that box. Okay, you understand how this cross has come? Because S0, it has got an S0 S1 conditions, whereas from here it is very clear S0 S1 cannot be done here, so there is a cross already here. Okay, now what is this? Is a tick. So no, then the next condition is S0 S3. Is there any in the leftover boxes? Now this is crossed. S0 S3, it's not there. So okay, now S0 S4. S0 S4 is also not available here. Now I come to the second column, S1. S1 S2 is also not permitted, right? S1 S2, you have a cross here. You have an S1 S2 out here, so let me put a cross there, right? Then S1 and S4, this is a conditional possibility, so we will leave it that. We come to S2. S2 S3, is there any S2 S3? It's not there. S2 S4, it's not there. So it's not there. So that's all. Now if you see, there is only one element which is left, which is S0 S2. It says if it is a conditional probability for S1 and S4 condition, if it meets this condition, S0 is equivalent to S2, then S1 and S4 can be merged. It says S0 and S2 is already merged here. That means this condition is also met. So now you can merge S0 and S2, or you can also merge S1 and S4, right? So there are two combinations can be made here. One is between S0 and S2, and the second one is between S1 and S4. So that is what it is done here now. So S0 has been merged with where it is, S0 is been merged with S2, so S2 has gone from here, and then you have the next condition. Okay, it's available here also. Okay, and the next condition was merging of S1 and S4. So S1 and S4, they have been merged together, right? So S1 is here, S4 has been removed. So accordingly this, so this is now how we have gotten using the implication chart method, we have simplified the sequential circuit out here. Okay, so that's all for today. In the practical tutorials, I will try to give you some more real life examples of how to optimize the sequential circuits. With that, your fundamentals on sequential circuits will become strong, and you will be able to handle any type of questions. Okay, thanks a lot.